So today I'm going to talk about SNSPDs and particularly how they can be beneficial to improving next generation quantum networks. So as Alex said, I actually last year started as a faculty at the University of Geneva, where I was previously doing my PhD, but also a lot of the content here will be about work that I did at the Jet Propulsion Laboratory, where I'm still a visiting scientist. So we're sort of kind of expanding the effort, and it's a very collaborative environment, which is great. So to give you a little outline, I'll first give a little introduction of the superconducting nanowire detectors. We'll look a little bit of how we've used these detectors to improve the qubit rate nanowire distribution. I'll also give a little bit of an overview of quantum key distribution efforts in Geneva. I'll talk about deep space optical communication, which was done at JPL. And then at the end, I'll also would like to highlight a few emerging capabilities of SNSPDs that I think everyone should be aware of. We can start kind of thinking about how we can use these detectors for future applications. So for those that have never heard of an SNSPD, this is a device that looks a little bit like this. So you a wire of superconductor that meanders back and forth, typically. So this is a case where you want to illuminate it with an optical mode perpendicular to the nanowires. So this is typically on the order of 10 microns, trying to fiber couple it. And historically, these wires have been very small. So this is a device that was actually made at MIT. It's very, there they had very good nanofab, and this is on the order of 60 nanometers. And now you'll actually see a few pictures. People have scaled these up to even larger. So you can actually do micron wide wires, which is quite remarkable. Only a few years ago, we thought that's impossible, but material improvement enabled that. The reason that SNSPDs have sort of advanced quite quickly is that the nanofabrication is relatively straightforward for like a device like this. So you deposit a superconducting film on top of a wafer, one step of etching, and you've got this nanowire. So it's very flexible. So there's a lot of research institutes around the world that can make these devices do sort of material development. Now they are getting more complex. You'll see later on the architectures are becoming much more complicated. So you maybe a much more advanced fabrication facility. But nevertheless, you can still do a lot of good research with these kind of simple approaches. So the way this detector works is that you start off with the superconducting film, and you put a current through it. Then the second step, your photon comes along and creates this sort of electron hole pair here, and you actually get a down cascade process where you break a lot of Cooper pairs. So at the end, you're left with thousands of normally conducting electrons. This is what sets these detectors apart from semiconductor counterparts, because semiconductor, you sort of start with one electron hole pair and you're trying to amplify that. Here, we break thousands of Cooper pairs. So it's really efficient and sensitive with that. The next step is actually sort of an ongoing topic of research. So there's actually some vortices that get involved and they start propagating across the nanowire, heating the device. So this is sort of second step of amplification. And then once you can actually break the superconductivity across the wire, you get this hot spot which expands lengthways. And this is what makes it sort of a digital detector. So every single photon, you get a digital click where the resistance is quite large. So you can model it like a switch in parallel with a resistor. So you get a click for every photon you absorb in the film. So I can show you later on some simulations of how they work if you want. But as I said, the sort of most interesting topic right now is understanding how these vortices propagate in nanowires. So there's still a lot of material science to be done. What's made these detectors very attractive for a lot of applications and advances that have been made in the last 10 years. So this is a table of the key metrics. So for example, the timing resolution, intrinsic photon number resolution, efficiency, array sizes, etc. As you can see, for example, the array size, as I said, 10 years ago, we were on the order of tens pixels. Now we've actually reached 100,000. So this is starting to get into the regime where we have, we're starting to compete with sort of CMOS cameras. And so this has really become quite exciting. The efficiency, this is the key thing that, was pushed in this forward. And this is really what kind of put these detectors on the map of quantum science. In quantum science, we don't lose any photons. But there are other things as well that you should be aware of, like, for example, cutoff energy of these devices is really remarkable. We've demonstrated single photon counting at 29 micron. So we're not going to talk about this in this talk, but for high energy physics applications and fundamental physics applications, this is really kind of quite exciting. So you can sort of start to group some of these metrics into like blobs and deciding, okay, for quantum science, we want, good timing resolution, photon number resolution, efficiency. So this is kind of where the research field is at right now. All of these demonstrations have been done independently. So taking one single metric, forgetting about the rest. We don't have a single device that can do all of this right now. And so we probably never will. But we can start to kind of group them together. So this is kind of what the field is working on right now, is like combining things together for quantum science, astronomy applications, biomedical imaging, remote sensing. They're very interested in arrays, high count rates, etc. As I say, energy physics is kind of becoming aware of these detectors as well. So, from that, you can kind of see how we try different things with these devices. So we can arrange the nanowires as a single pixel. So this is just one of these meanders. You get high count rates, which you'll see later on. We actually interleave these devices together. So this is 4 SNSPDs covering one single optical node. So then you can increase your count rate by a factor of 4. We now have started making large arrays. So this is a case where you have these kind of 1 micron wide wires. Here, this is a device that covers 1 millimeter area. So it's kind of getting into a regime of a PMT. It's quite interesting. And then obviously people want to start imaging. So this is a pixelated detector. And the other thing that's very exciting for quantum science is waveguide coupled. So with one, this is kind of what's the power of these devices, because it's just a wire, shape it however you want, put it on many different materials as you wish. So in terms of the established applications already, we have sort of quantum information science, which is really where this got pushed to the beginning with deep space optical communication. This is something that I'll talk about in a bit. This has really enabled a lot of breakthroughs for SNSPDs, sort of pushed by NASA for the last 20 years. And the things that are emerging now is astronomy, physics applications. So people want to use cameras of SNSPs for exoplanet searches, far infrared astrophysics, etc. And then biomedicine and physical chemistry also, they're typically operating at wavelengths that people don't think about. So now that these detectors are really broadband, you can really go to these folks and say, like, right, what camera do you actually want to fabricate for? So this talk, I'll concentrate on quantum communication and deep space optical comm. And if you want to ask questions about any of the others, reach out. So yeah, let's kind of switch gears and think about what we want from a detector. We want to do quantum communication, right? So if we're doing quantum communication with photons, we've got Alice, Bob trying to talk to each other through the quantum channel. One of the most practical sort of encodings for this scheme would be time-bit encoding. So this is where you encode a 0 or a 1 early or late photon. And then you could, for example, look for the eavesdropper by adding the second state, which is a superposition of early and late. So now sort of ask ourselves, what do we need from this detector? First thing is we want high efficiency. We don't want to lose all our photons at the very end. We'll reserve that for the quantum channel. And we don't want any dark counts, because any dark count here would create a bit error rate. Now, the timing accuracy, this is something that we'll talk about quite a bit here. This is going to tell us what's the separation between this early and late bin that we can actually do on the source. And actually, probably heard about all the thin-film lithium niobate work. We can really have hundreds of gigahertz of bandwidth on our sources. So actually, the limiting factor is always the detectors. These kinds of systems, we will say like, right, how good is the detector? And we'll design the source around that because never really limited by that. And obviously, finally, if you want to repeat this experiment and get a big key rate for quantum key distribution, for example, you want to be able to count very fast. So the recovery rate is very important. So one thing that when I was at JPL, we worked on understanding the fundamental limits of the timing resolution. So this was sort of how close can we get these two time bins next to each other, with particularly looking at the nanowire. So this was a really big collaboration with MIT and NIST, JPL. So we made these devices which were very short nanowires. So they were only 5 micron long because we wanted just to see how good is the timing resolution, this very small, high quality device. And what we found is that we actually, for the first time, started to probe the timing resolution for different wavelengths of photons. So we could see that, you would kind of intrinsically imagine that lower energy, worse timing resolution, because if you deposit no energy, you never know anything, right? So the higher the energy, the better time resolution. This is kind of what we saw. And, you can actually get down to less than 3 picoseconds for visible photons. And in the telecom range, this is on the order of 4.3 picoseconds. So this is already, was quite impressive. It shows that we could push communication rates to very high. We actually did a proof of principle experiment where we collaborated with UCSD. They were at the time working on these thin-film lithium niobate modulators. And so they had a modulator that they believed could modulate at 100 gigahertz, an optical waveform. And the only way they could characterize it was with a bit of a spectrum analyzer. So they actually brought it to our lab. And we managed to make a optical sampling oscilloscope with this single photon detector. So imagine if you sort of synchronize your modulator detector, start picking out single photons from the waveform. That is an optical sampling oscilloscope. So after a while, once you collect your histogram, you actually get the waveform of 100 gigahertz. So this is really 10 picosecond time scale. So this is, we believe, could be a really good application for these detectors in the future, specifically for characterization of high-speed modulators. Especially, it's not necessarily going to be better than a classical optical sampling oscilloscope, but the dynamic range and sensitivity of this is at the single photon level. So if you have a very weak waveform, it'd be a nice way of doing it. So this is not a, sort of proof of concept demonstration. The efficiency of this particular detector is not very good because it's very small. So the next thing we wanted to do is actually figure out a way to increase the active area of these detectors, to make them efficient. Efficiency was one of the metrics in our sort of prerequisites. So now we've gone back to the meandered structure where we can actually optically couple our fiber mode perpendicular to this nanowire. Now, what actually happens is that you get a sort of timing distribution depending on where the detection event actually happens. So you get this kind of thing called geometric jitter. So in order to cancel that out, this was actually a technique that was invented initially at MIT. They realized that we detect the two sides of the nanowire cancel out these geometric effects. So what we did here was actually impedance match both ends of this nanowire. And this allows you to do cancellation of this geometric effect. So devices were actually made in a really sort of practical package. So it's fully fiber coupled here from the top. And we've got our two ends of the device. And this kind of detector has already been deployed in many labs. So we kind of tried to make it as deployable as possible with multiple applications. And so we want to look at the overall metrics. So we could get efficiency, so not the record, but 80%. So it's good for quantum com application. Dark count rates, fiber coupled case, you can have sort of tens of counts or one count if it's fiber coupled. The timing jitter here, this is sort of what we're concerned with mostly, is around 13 picoseconds full width half max. So it's not as good as the sort of short nanowire, because now we have sort of more probability of having an imperfection along the wire, so we can't quite get to the same critical current. But it's still very good. So actually, the most important thing is not necessarily if you buy a detector from someone, say, or you place an order for an SNSPD, and ask them what the jitter is, don't ask them what the full width half max is, ask them what the full width over 100 max is, because that's actually what's important for quantum communication. This is essentially sort of 1 over 100, which is going to be kind of like your qubit, right? So if you get a detection here, it means you sort of have less than 1% chance getting it in that neighboring time bin. Whereas if you set your time bins at the full width half max, you'll have 50% error rate. It's kind of one way to think about it. So this is sort of saying that 1 over this value is the maximum possible clock rate of your quantum key distribution system, for example. So in this case, 20 gigahertz. So this is what we kind of started off with. We're like, right, this is how a detector works. Now let's design our quantum key distribution or quantum entanglement distribution systems around that. Yeah, one other thing as well, I wanted to highlight, we actually did an experiment to show that you can actually get very low dark counts or free space coupled system. So we actually took this detector and we put it in a free space coupled cryostat and optimized the filtering. Turns out the 1550 is quite hard. We have to sort of combine a bunch of short pass filters, like 2 different short pass filters and a band pass filter. You can actually achieve dark count rates which are better than a fiber coupled system, 10 to the minus 1 counts per second, whilst maintaining sort of high efficiency on the order of 70%. So this is something that's quite promising, again, for kind of free space quantum comp in the future. Right, so actually, now we've got our detectors, let's try and do some quantum communication with them. So one system that we set up at JPL was trying to do some entanglement distribution. So here we have pulse laser, it's converted to 775, and then we do spontaneous parametric down conversion, where we're able to split the 2 photons to Alice and Bob using a wavelength-division multiplexer. So the idea here is that pairs are sort of paired up in DWDM channels, so we can actually create many channels simultaneously. And in this case, we really try to go at a clock rate that's demonstrating showcasing the timing resolution of these new detectors. So in this case, you can see our time bin qubits are formed with an 80 picosecond separation. So you can actually see that we can clearly resolve these multiple pulses, which are separated by 80 picoseconds. So this is the appearance bin here, and this is sort of the early and late. And then in this case, we didn't do sort of a demonstration where all of the channels are running simultaneously. We just sort of went through each channel individually just to check how good the quality is. But you can actually see that you have this sort of coarse JSI where this is sort of the coincidence rates in the middle here, hertz. So it works really well. And the visibility of the system is extremely good, because it turns out that if you make these time bins very close together, the interferometers become very small. So the separation of 80 picos is just 80 centimeters. So there are really good interferometers in this range. They're made for the telecom industry already. They're even space qualified. And you can just put them on the table, super stable, with kind of a thermal design. So you can get very high visibilities, but you really have to run at this high clock rate and have low timing jitter. So this table kind of just shows a little sort of summary of, let's say, if you were trying to do quantum key distribution with these entangled pairs for a single channel, you can actually reach at zero loss about 0.3 megabits per second, which is pretty high. And so then we just sort of extrapolated, because in principle, we have access to all these other pairs of photons. So if you had an array of detectors, or many of these single-photon detectors, if you went to 60 channels, you could have 14 megabits per second. And another way to look at it is sort of spectrum of the photons. So this is the spectrum of all of the entangled photons. So it's actually on the order of 100 nanometers wide. And this is sort of, this dark band here is what we characterized in this experiment only. So we're not even getting, even in this experiment, we didn't use everything we have. So the way we see it is that in the future, we want to enhance this by using arrays of SNSPDs. So you can actually imagine having our entangled photon pair source here. We split the photons with a dichroic mirror. And on one side, we put some diffractive optics and put it onto an array of SNSPDs, because fiber coupling 60 channels requires that. I wouldn't want to make a student do that, but doing this kind of thing would be more fun, I think. So, right, and then, let's switch gears a little bit to quantum key distribution. So this is actually highlighting more of the work that's been I've been doing in Geneva during my PhD, and kind of taking over again now. So there we also develop sort of high frequency quantum key distribution systems. And the protocol that we use there is a sort of a simplified BB84 protocol. So the simplification comes from removing one of the states. So actually it turns out that a few papers 5-6 years ago which showed that you can actually achieve basically the same secret key rates by removing one of the states. So effectively, this basis here becomes the key generation basis. So this is where you encode your 0 and 1. And then this additional state here is what actually checks the security of the protocol. And you don't generate any key, obviously, in this basis, because you don't have the other bit. But you can actually achieve the same performance as a 4-state BB84. So in this case, we start with a pulse laser, and we create time-bend qubits. So right now, here we actually stick with 400 picoseconds, because we haven't yet sort of scaled up these low jitter SNSPDs so far. And from time to time, we actually want to compare and benchmark these systems with in-gas detectors. They just can't have that kind of timing resolution so far. So it gives us more flexibility. And then we, create a superposition with the parameter. So this kind of modular R&D platform gives us a lot of flexibility, and the system's been used to set a lot of records at the time. It's been beaten since. So, for example, with the managed to get 64 megabits per second at 10 kilometers. It's been surpassed by John Wei Pan's group by about a factor of 2, but it's still up there, and we want to kind of keep going and push it to further high rates. Distances for the system has also been achieved to 420 kilometers. This has, of course, also been surpassed already with sort of twin field QKD experiments, but this is much more practical in principle. The direction we're sort of starting to go in now is starting to integrate many of the components as we can with integrated photonics. So, in the future, we really want to reduce the scale of these devices to have like low swap systems, maybe even just small factor pluggable systems. But, there's a lot of stepping stones for that. So this particular project here was try to integrate at least some components. So here you've got sort of inactive components in a PIC, and also the passive interferometer in a PIC. So, here, this is the actual PIC in a 19-inch rack system. So you can see that actually the bulk of it is still PCBs, FPGAs, but see if you actually start to stack all of this on top of each other, you could get a nice little cube feature. Here in the Bob, you have in-gas detectors actually. So again, it's very compact, much more compact than SNSPDs. So this is something that could also kind of have a cube. The main thing is that you can actually sort of get rid of these detectors and plug in SNSPDs if you want. There's got a lot of modularity. So we'll zoom into the transmitter. This is using silicon photonics at the moment. We do actually want to switch to thin film lithium niobate, because we think much better performance and sort of more stability. On the receiver side, this is silica-based interferometers. Again, this has been working pretty well. So we actually sort of test these devices of coordinate key distribution in a network that we recently launched in the Geneva area. So this is the Geneva Quantum Network. It's a little bit further behind than your guys' quantum network. We only started in January and not quite as much distance yet, but it's a stepping stone that we hope will cover most of Switzerland actually in the next few years. What's really cool is that we have a lot, so started in January, we could see a lot of interest. So we already have CERN that's very excited about quantum technologies. To our surprise, even Rolex kind of signed up and they want to test some sort of atomic clocks that they're developing, distribute timing across this network. We also have universities of applied sciences, which are really taking these technologies seriously. And of course, ID Quantique is just over the road. So far, we've actually done a couple of demonstrations of quantum repeater node between our two university sites. And this particular graphic here is showing this rack-mountable QKD system running with around 1 kilobit per second looped back from these two sites. Again, this is with SPAD, so this is what's limiting the rates at the moment. So now that it's been sort of tried and tested, the next steps for us is to actually deploy these high-rate SNSPDs and see how far we can push it. So now let's switch gears a little bit to deep space communication. And this is going to be actually fully classical at the moment. But I think, I hope I can convince you that a lot of the sort of lessons learned from some of these demonstrations can be applicable to quantum communication in the future. And this is what we kind of see happening in the future. So over the last 20 years, as I mentioned at the beginning, NASA actually invested a lot of money in developing deep space optical comm. And the reason for this is to actually just increase the data rates that science missions can achieve from just spacecraft. So for example, there's a Psyche spacecraft that wanted to study an asteroid in the asteroid belt, and to increase the data throughput just for the number of images it can take, the spectra it can take, you really need to boost the data rates to radio. So the way we actually do this is encode the data time bins again. So this is not a time bin qubit, it's a time bin pulse. And so the way you do it is you sort of separate out lots of time slots and you send one pulse in one of these time slots. So this encodes sort of a word. And it turns out that you can actually get very high photon efficiency. You can encode more than 1 bit per photon detected. And it really sort of saves power once you really go far away from Earth. And so now, why do we need single photon detectors? On the spacecraft, you would start with a lot of photons. So there's actually 10 to the 19 photons per second generated by the laser. But by the time the spot gets to the Earth, it's the size of California. And so that's about 1 megaphotons per second collected by a 5-meter telescope. So you can see this is a completely photon-starved regime, and you really need to count every single photon. And so we set out to deploy SNSPDs on some of these telescopes around the US. And actually, now there's even some efforts in Europe as well where there are SNSPDs being deployed. So if we kind of zoom in to see what some of these detectors look like, in this case, we really want to kind of have a bucket detector. So we have a large active area. So this one, for example, is 300 micron in diameter with 64 wires. And this is the one that was deployed on the 5-meter telescope. But there are actually 3 other stations already US that have SNSPDs from JPL. So one at Table Mountain, which is a very good, this is actually a very good telescope for quantum communication because it can track low Earth satellites. This has the same size of an array there. And then with MIT Lincoln Lab collaborated, and they actually deployed SNSPDs on a smaller aperture telescopes. And this was a sort of very ambitious project where that were deployed together with the radio dish. So sort of mirrors inside the radio dish demonstrate both RF and optical at the same time. So this is what a system like this looks like at a telescope. So at Palomar, you have the two-day focus here. So this means that perhaps that doesn't have to move, which obviously is good. But this just goes to show that it is possible. So this was a system that was very heavily engineered. So you have 64 coaxes coming out. This is a free space coupled cryostat. So it just shows that it is possible to deploy SNSPDs on a telescope, and it's very stable. And now we're trying to sort of minimize or miniaturize all of these components, just systems. This kind of just shows that all of these 64 detectors, they work with saturated efficiency, around 70%. And to sort of summarize the overall mission, this was actually launched in 2023. The final preparations of this was actually happening in COVID. There was people still going into JPL and putting this thing together, which is quite remarkable. Launched on a SpaceX rocket in 2023. And this is the trajectory. So it goes from Earth, does a bypass of Mars, comes close to Earth again, flies off to the asteroid belt. So this actually every single Monday, the team at JPL, they went and sort of collected data to see how fast they can board or download information. So this, you have to kind of decide on what's the first thing you want to send. And obviously it's a cat video. So this was the furthest cat video ever sent, 30 million kilometers. So this was this was kind of uploaded onto the spacecraft and then downloaded through this link. And they kind of tested it at different ranges. So you can actually get 260 megabits per second, 0.4 AU. And then at sort of Mars equivalent range, you still have 25 megabits per second, which is really cool. So this is something that will boost the science rates in the future. Or if you've got astronauts that go into Mars, you're going to have sort of video constantly being streamed. So we can actually see kind of Big Brother style what they're doing. So kind of the motivation. So switching gears a little bit, I really want to talk about these kind of emerging applications of SNSPDs, and so that we can start thinking about what we can do, look out for. So one thing is actually photon number resolution. Actually, Dee, when he was back at MIT, he did a really nice proof of concept demonstration, which showed that the rising edge of these SNSPDs can encode photon number resolution, photon number information. So we actually took this approach and we combined it with our sort of differential detector that gets rid of the timing resolution, smearing, and boost the efficiency a little bit. So we could really see this very clearly. So these are kind of like blobs of post-processing data, looking at these timing resolution or rising edge slopes. So you can really see a blob for 1 photon, 2 photon. It starts to kind of smear off at higher photon numbers. So you kind of really want to use this detector to distinguish between 1, 2, or maybe 2 or more photons. And if you actually wanted to have more photon resolution later on, you'd want to start making arrays of these. But it does work very well. So a lot of people are excited about this. And some of the challenges now is just to really combine this with ultra high efficiency. So at the moment, this is only 80, 85%. We really need to get it to 95, 98% to make it interesting for quantum optics. Another thing that we actually did was just to figure out what is the absolute sort of fastest we do this deep space optical comm. So for this current kind of cat video I showed you from deep space, the time slots were only 500 picoseconds, but we wanted to do a sort of test bench demonstration using these detectors to see if we can improve that by an order of magnitude, increase the data rate even more. And it turned out that you actually wanted to use this photon number resolution of the detectors correct for time smearing in the signal itself. So you can see that you don't use this rising edge corrections. You get a really ugly set of histograms, which would be fine for a 500 picosecond slot. But if you want to do 50 picoseconds, you really have to take care of this photon number kind of distribution on the detector. And so the PhD student at the time knew that he actually managed to demonstrate this and really run it at 20 gigasamples per second with good error correctable rates. So this was actually an image of the Mars rover encoded with this detector, reconstructed it. So this is with no error correction, still able to recover the data system at 20 gigahertz per second. So this kind of is a sort of like a preview that you could also do quantum comp at those rates if you wanted to. Another thing that we're working on a lot is increasing the count rates of these detectors. So if you did want to do let's say entanglement swapping with satellites in the future, really high clock rates, you really need to get to the gigacounts per second rates on the ground. So the way you do that is that you need to actually make arrays of SNSPDs. One single detector so far can only count at maybe 10 to 100 megacounts per second. So it's actually rather straightforward. You can sort of create an array of high count rate SNSPDs. So in this case, this is just a bunch of straight lines coupled to a single optical mode and demonstrated 1.5 gigacounts per second with the system. So this is sort of one wire count rate. Then this is the full wire count rate, 1.5 gigacounts per second. So if you want to do ultra high speed quantum comp, this is kind of what you need to do. And the other thing I just want to sort of finally highlight is the development efforts to really make cameras as well. So you can sort of have this sort of tens of pixels with dedicated readout. And one thing that we were thinking about a lot at JPL and NIST was actually how to make an array of these detectors. So the scheme that we came up with is actually coupling these SNSPDs to a readout bus. And in this case, this is effectively just another superconductor. Imagine you have a superconducting bus over here, and this SNSPD current pulse actually goes into a nanofabricated resistor. When this resistor fires, it actually breaks the superconductivity here, and you can create a differential signal. So again, this is very much along the lines of being inspired by this differential readout of the SNSPDs. And so you then can actually resolve where along this wire this event happened. You can tell which pixel fired from that. We call this kind of thermally coupled imager. And I won't go into detail of this. You can sort of pull me over later on. But the basic principle is the same. You can actually sort of use this thermal coupling to couple a lot of wires against each other. And the main sort of demonstration is that a few years ago, NIST and Boulder, they actually managed to demonstrate 400 pixels using this kind of thermal coupling approach. So in this case, this is a proof of concept where essentially have these pixels demonstrated by crossing areas of these wires. So you've got kind of few micron pixels. And right now, the efficiencies are not super high because it's just the very first proof that you could get to these large pixel numbers. The count rates are limited because you've got so many. But this is all problems that are kind of working on right now. And we're working on as well to sort of scale up the count rates, the efficiencies. Well, so this is something that is actually becoming very exciting for new astronomy applications, but also for optical readouts of quantum computers. So for example, if you have ions, an array of ions, you want to read out an array of neutral atoms, you want to read out, you can actually count photons with this kind of camera very fast. So we're very excited about that for the future. And so I'll kind of leave you with this. This is current records for SNSPDs on individual metrics, but as a community, we really think this is really not over. We've got so much more room for improvement. So this is kind of our guesses in the next 10 years of where we think we can get to. We're going to keep ourselves nice and busy. So yeah, with that, I'll kind of wrap up. And, thanks to my colleagues. So this is sort of the team at University of Geneva working on the quantum communication and SNSPDs now. Sort of our department collaborators working on all sorts of theory, quantum memories, etc., which form this really nice environment in Geneva. And then also my colleagues at JPL, MIT, NIST, whom this wouldn't have been possible. Thanks a lot.